You are listening to the Architectural Compass, navigating monoliths, microservices, and the future of software. Like and subscribe to keep up to date on our latest audiobooks. The Architectural Compass, navigating monoliths, microservices, and the future of software. Chapter 1, The Architectural Crossroads, Shaping the Digital World. Welcome to the fascinating world of software architecture, a realm where technology meets strategy and technical decisions profoundly impact business outcomes. If you've ever wondered why some software systems seem to scale effortlessly to millions of users, while others creak under the strain of just a few thousand, or why some companies can release new features daily while others take months, you're looking at the direct impact of architectural choices. At its heart, software architecture is the fundamental organization of a computer system. It's like the blueprint for a building, but for a digital one. It defines the major components of the system, their relationships to each other, and the guiding principles behind its design and evolution. Just as an architect designs a home with consideration for its eventual inhabitants, their needs, and the very ground it stands upon, a software architect plans a system based on its purpose, its users, and the technological landscape it inhabits. A well-designed architecture provides a stable and efficient foundation. A poorly chosen one can lead to constant struggles, missed opportunities, and eventually, a costly rebuild. For many years, the standard approach to building software was to create a single, unified application responsible for all its functionalities. Imagine a bustling factory where every single production line, from raw material intake to final product packaging, is housed under one massive roof. If you need to make a small change to how one product is assembled, you might disturb and even temporarily halt other operations across the entire factory. This approach in software is known as a monolithic architecture, a single, tightly integrated application with all its parts contained within one codebase and deployed as one unit. It was, and still is, the default for many projects, especially in their early stages. For simpler applications or small, focused teams, a monolith offers a straightforward path, allowing for quick initial development and simpler deployment. However, as businesses demanded greater agility, faster innovation, and the ability to serve millions or even billions of users, the limitations of this single factory model began to show. Adding new features became slower, scaling individual parts of the system was impossible without scaling the whole, and a problem in one area could jeopardize the entire application. The demand to evolve faster than the factory could handle, coupled with the need for systems that could endure constant pressure with minimal downtime, led to a different way of thinking. This pressing need for agility and resilience paved the way for a new architectural philosophy: microservices. Instead of one giant factory, picture a vibrant city composed of many specialized businesses. There's an independent bakery, a separate logistics company, a dedicated payment processing office, and so on. Each business operates autonomously, focusing on its specific function. They communicate and collaborate to provide a complete experience, but each can adapt, scale, or even be rebuilt independently without disrupting the others. In microservices, an application is broken down into a collection of small, independent services, each responsible for a specific business function. Each service can be developed, deployed, and scaled independently, offering unprecedented flexibility and resilience. The debate between monolithic and microservices architectures isn't just technical jargon. It's a strategic conversation that every modern organization grapples with. It impacts how teams are structured, how quickly new products can be launched, how reliably systems operate, and ultimately, a company's bottom line. It's important to understand upfront that there's no universal, better option. Neither monoliths nor microservices are inherently good or bad. Instead, the ideal choice depends entirely on your specific context, your team's capabilities, your budget, and the unique demands of your business goals. Choosing the wrong architecture can be more detrimental than choosing the suboptimal one for your situation. Throughout this book, we will demystify these two major software architectural philosophies, exploring their distinct strengths and weaknesses. We'll delve into the real-world experiences of companies that have made these choices, the challenges they faced, and the strategies they employed to succeed. This journey will guide you through the fundamental principles of each style, help you recognize when a change might be necessary, and provide practical, step-by-step strategies for transitioning between them. Whether you're a developer choosing your next project's foundation, a project manager assessing your team's agility, or a business leader aiming to leverage technology more effectively, understanding these architectural patterns is crucial. By the end of this book, you'll possess an architectural compass to chart your course in the ever-evolving landscape of software, enabling you to make informed decisions that align technology with your strategic objectives. Let's begin our journey. Chapter 2, Understanding the Monolith, the Tried and True Foundation. Before we can fully appreciate the nuances of modern software architecture, it's essential to understand the foundation upon which many systems were built, and indeed, continue to be built today. The monolithic architecture. What is a monolithic architecture? At its core, a monolithic application is designed as a single, indivisible unit. All the user interface, business logic, and data access layers are intertwined within a single codebase and deployed as one large artifact. Think of it like a traditional single-story house. All the rooms, kitchen, bedroom, bathroom, living room, are contained within one structure. When you modify one room, say the kitchen, it's part of the same overall building project. Similarly, in a monolithic application, if you need to update one small feature, you typically rebuild and redeploy the entire application. Historically, this was the standard way to develop applications. Most early web applications, enterprise systems, and desktop programs were built this way. It's a natural starting point when a system scope is relatively small or well understood, and the initial team developing it is compact. The genesis and appeal of monoliths. The appeal of the monolith is immediate and intuitive, especially in the early stages of a project or for applications of modest complexity. Simplicity during initial development. Getting started is straightforward. You typically set up a single development environment, use a single repository for all your code, and work within a unified framework. This simplicity means you can often build and launch a basic version of your application very quickly. Unified tooling and environment. All developers work on the same code base using the same set of tools, libraries, and frameworks. This reduces setup complexities and streamlines collaboration for small teams. Simpler deployment. When it's time to release your application, there's only one artifact, a single web archive file, an executable, or a directory to deploy. This simplifies continuous integration and continuous delivery, CI/CD, pipelines in the early stages, as you're managing only one release process. Local debugging and testing. Debugging is often easier because all components run within the same process. You can step through code seamlessly from one functional area to another. Testing is also simplified as you generally have a single set of unit, integration, and end-to-end tests that interact with the complete application. Fewer cross-cutting concerns. Managing aspects like transaction boundaries, logging, security, and caching is often less complex in a monolithic application because these concerns operate within a single process boundary. A database transaction, for example, can easily span updates across multiple logical components. Consider a small e-commerce website designed to sell a specific niche product. Initially, the team is just a few developers. They can quickly build the product catalog, user authentication, shopping cart, and checkout process all within one application. Their users are limited, and traffic is low. In this scenario, the simplicity and speed of a monolithic approach are clear advantages. The growing pains, disadvantages of monolithic architecture. While the early benefits are compelling, the elegance of the monolith often fades as an application grows in size, complexity, and user base. The very characteristics that make it appealing in the beginning can turn into significant drawbacks, leading to what is often described as growing pains. Scalability challenges. One of the most common issues is scaling. If only one small part of your application, say the product recommendation engine, experiences a sudden surge in demand, you still have to scale the entire application. This means deploying more instances of the entire monolith, even if the other parts are underutilized. It's like needing more cooking capacity in your kitchen, but the only way to get it is to build an entirely new house with a new kitchen, new bedrooms, and everything else. This can be inefficient and costly. Developer productivity slowdown. As the codebase swells to hundreds of thousands or even millions of lines of code, several problems arise. Longer build times. Compiling and packaging such a large application takes increasing amounts of time, slowing down development cycles. Increased complexity. It becomes difficult for a single developer to understand the entire application. Changes in one area might inadvertently break functionality in another, leading to a fear of making changes. Merge conflicts. With many developers working on the same large code base, frequent and difficult code, merge conflicts become common. Onboarding challenges. New developers take a long time to become productive as they struggle to grasp the vast and interconnected codebase. Technology lock-in. Once you commit to a specific technology stack, e.g., Java with certain frameworks, or a particular version of a scripting language for your monolith, it becomes incredibly difficult to introduce new technologies or upgrade existing ones. Porting the entire application to a new stack is a Herculean task, often making companies hesitant to adopt more modern, efficient tools. Deployment bottlenecks. Even a simple change, like fixing a typo on a web page, typically requires rebuilding and redeploying the entire application. This can lead to slow release cycles, reduced agility, and a lack of confidence in frequent deployments. The risk of the entire application being down during deployment is always present. Reliability risks. In a monolith, if one component fails or has a memory leak, it can potentially bring down the entire application. This single point of failure makes the system less resilient. For instance, if an e-commerce monolith's payment processing module crashes, the entire website might go offline, affecting product browsing and order management too. Maintenance headaches and vendor lock-in. Over time, a monolith can accumulate technical debt, shortcuts taken, outdated libraries, poorly structured code. Untangling this spaghetti code can be incredibly difficult. Furthermore, if you rely on a specific vendor's proprietary systems, you might find yourself stuck with their ecosystem due to deep integration within your single application. The big ball of mud syndrome. Without disciplined architectural oversight, large monolithic systems often evolve into what's colloquially known as a big ball of mud. A system lacking a discernible architecture, where everything is connected to everything else in an unmanageable tangle. Logic is duplicated, boundaries are blurred, and change becomes agonizingly slow. When to choose or stick with a monolith. Despite its potential pitfalls at scale, the monolithic architecture is far from obsolete. In many scenarios, it remains a pragmatic and efficient choice. Small, simple applications. For applications with limited functionality and a small user base, the overhead of a distributed system like microservices simply doesn't make sense. You can get to market much faster and with less complexity. Startup and early-stage projects. When a startup is trying to validate a new idea, speed to market is paramount. A monolith allows teams to iterate quickly, gather feedback, and pivot if necessary without significant architectural investment. The focus is on proving the business concept, not on building an infinitely scalable architecture from day one. Applications with tightly coupled functionalities. If all parts of your application are inherently and deeply reliant on each other with no clear boundaries for separation, then attempting to break them into microservices might be an exercise in futility, adding unnecessary complexity. Teams unaccustomed to distributed systems complexity. Building and operating microservices requires a different skill set and an organizational culture that embraces distributed thinking, automation, and operational responsibility. If your team lacks this experience, starting with a monolith is safer. You can always evolve later. Consider our e-commerce example again. For that small, niche product store, a monolith is likely the correct technical choice. The team is small, the features are well-defined, and the traffic is predictable. Trying to build it as microservices would introduce unnecessary complexity, slowing down development and increasing costs without providing commensurate benefits. In summary, the monolithic architecture is a powerful and viable choice, particularly for applications in their infancy or those with well-defined, stable requirements. It offers simplicity, faster initial development, and ease of deployment. However, it's crucial to be aware of its potential limitations as an application grows. Understanding these trade-offs is the first critical step in making informed architectural decisions for your software's journey. Chapter 3: The Rise of Microservices, Specialized, Scalable, and Agile. As the demands on software systems grew exponentially, from simple websites to global applications serving billions of users daily, the limitations of the monolithic architecture became glaringly apparent. This push for greater agility, enhanced scalability, and improved resilience led to the emergence and widespread adoption of microservices. What is microservices architecture? In stark contrast to the monolithic approach, a microservices architecture breaks down a large, complex application into a collection of small, independent, and loosely coupled services. Each service is designed to perform a single, specific business function, or, more broadly, to operate within a very well-defined, bounded context. Imagine our previous analogy of a single, general-purpose factory. Now, instead, picture a meticulously planned city. This city isn't just one giant building. It's a collection of many specialized buildings, each with its own function. There's a dedicated power plant, a water treatment facility, an accounting office, a delivery service, a customer support center, and so on. Each building operates independently, has its own staff and resources, and communicates with other buildings only when necessary, through clearly defined channels, like postal services or telephone lines. This city represents a microservices application. Each building is a microservice. Key characteristics of these specialized buildings or services include autonomous and independent. Each service can be developed, deployed, and managed independently of the others. A change in one service doesn't necessarily require rebuilding or redeploying the entire application. Communicates via APIs. Services interact with each other through well-defined application programming interfaces, APIs, typically using lightweight mechanisms like HTTP, REST, or message queues. This loose coupling is critical, organized around business capabilities, rather than being divided by technical layers, like a database service or a user interface service. Microservices are typically organized around real-world business functions, such as an order processing service, a customer management service, or a product catalog service. Decentralized data management. Each microservice often owns its own data store. This prevents direct database coupling between services, which is a common source of friction and dependency in monolithic systems. The drivers behind microservices adoption. The movement towards microservices wasn't driven by a sudden technological fad, but by genuine pain points experienced with large monoliths. Need for agility and rapid deployment. Businesses needed to respond to market changes faster. Monoliths, with their long release cycles, hindered this. Microservices allow small teams to develop and deploy features independently, significantly accelerating time to market. Solving monolith scalability and maintainability issues. As discussed in Chapter 2, monoliths struggle with efficient scaling and become increasingly difficult to maintain. Microservices address this by enabling individual scaling and breaking down the application into manageable pieces. Evolution of cloud computing and DevOps. The rise of cloud platforms like Amazon Web Services, AWS, Microsoft Azure, and Google Cloud Platform, GCP, provided the flexible infrastructure needed to deploy and manage numerous small services. Concurrently, the principles of DevOps, emphasizing automation, collaboration, and continuous delivery, provided the cultural and operational framework to make microservices feasible. Core principles of microservices. Beyond their fundamental definition, microservices adhere to several core principles that guide their design and implementation. Single responsibility principle. Just as a well-designed function in programming does only one thing well, a microservice should ideally be responsible for a single business capability. This limits its scope and complexity. Bounded context. Originating from domain-driven design, DDD, this principle emphasizes clear boundaries between services. Each service operates within its own explicit context, where terms and concepts have unique meanings, preventing ambiguity and tight coupling. For example, customer in a billing service might refer to slightly different data than customer in a marketing service. Independent deployment, a crucial principle. Each microservice should be deployable independently of other services. This means a bug fix or new feature in one service doesn't require redeploying the entire application. Decentralized data management. Instead of a single, shared database, each microservice owns its data. Whether it's a relational database, NoSQL data store, or even a simple file system. This allows services to evolve their data models independently. Resilience and fault isolation. If one microservice fails, it should ideally not bring down the entire system. Services are designed to handle failures gracefully, perhaps by degrading functionality or retrying operations. This prevents cascading failures. Technology heterogeneity. Unlike monoliths, where the entire application is often built on one technology stack, microservices allow for polyglot programming and polyglot persistence. You can choose the best programming language, framework, and database for each specific service, leveraging the strengths of different technologies. Advantages of microservices architecture. Adopting a microservices architecture, when done correctly and for the right reasons, can yield significant benefits. Improved scalability. This is a major advantage. You can scale individual services based on actual demand. If your product catalog service experiences a spike in traffic, you can deploy more instances of only that service, saving resources and cost compared to scaling the entire monolithic application. Enhanced agility and faster time to market. Small, independent teams can develop, test, and deploy features for their specific services much faster and more frequently. This accelerates innovation and allows businesses to respond quickly to market changes. Technology flexibility. Teams have the freedom to choose the most suitable technology stack for each service. This can lead to more efficient development, better performance, and the ability to attract diverse talent. Better fault isolation. A failure in one service is less likely to impact the entire application. If the recommendation engine crashes, users can still browse products and complete purchases. This improves the overall robustness and resilience of the system. Easier maintenance. Smaller codebases are inherently easier to understand, refactor, and maintain. New developers can get up to speed on a single service much faster than on a giant monolith. Team autonomy. Microservices promote smaller, cross-functional teams, often called two-pizza teams, meaning a team small enough to be fed by two pizzas. These teams own their services end-to-end, fostering a sense of ownership, responsibility, and faster decision-making. Resilience. The system can be designed to degrade gracefully during failures. For example, if a recommendation service is down, the system might simply not show recommendations, rather than crashing entirely. Consider Netflix's journey. Starting as a streaming video provider with a significant monolithic application, they famously migrated to a microservices architecture on Amazon's cloud platform. This transition was driven by their need to handle massive, unpredictable traffic spikes, ensure extreme resilience across diverse devices, and enable rapid innovation for their global service. Their experience is a prime example of how microservices can unlock the ability to operate at a scale and agility that would be near impossible with a traditional monolith. While microservices offer compelling advantages, it's crucial to remember they introduce their own set of complexities as well. Deciding between a monolith and microservices is not about choosing an inherently better architectural style, but rather about selecting the one that best fits your specific needs, capabilities, and strategic goals. We will delve deeper into these complexities in upcoming chapters. Chapter 4, a head-to-head comparison, choosing the right path. Having explored both monolithic and microservices architectures individually, it's time to put them side by side. The goal here isn't to declare a winner, but to provide a comprehensive lens through which you can evaluate which approach aligns best with your specific circumstances. Remember, context is king. Direct comparison, a side-by-side view. Let's compare the two architectural styles across several key dimensions. Feature dimension, monolithic architecture, microservices architecture. Simplicity, simpler to develop and deploy initially. More complex in development, deployment, and operations due to distributed nature. Initial development, faster to start, single code base. Slower to start, requires more tooling setup, distributed communication patterns, and infrastructure. Long-term development becomes slower as codebase grows, high coupling. Potentially faster as independent teams work on smaller codebases, low coupling. Deployment, one single artifact to deploy. Longer deployment times. Many independent services to deploy. Faster per service deployment, but complex overall orchestrating. Scalability, scales as a whole, vertical or global horizontal. Scales individual services, horizontal, component level, efficient resource utilization. Reliability resilience, single point of failure, a flaw can bring down the app. Fault isolation. Failure in one service doesn't necessarily impact others, degrades gracefully. Technology flexibility low, difficult to change introduce new technologies. High, allows polyglot programming and persistence. Can use the best tool for each specific job. Team structure and agility larger, integrated teams, slower decision-making. Smaller, autonomous cross-functional teams, faster decision-making, increased agility. Complexity, internal code complexity. Big ball of mud, risk. Distributed system complexity, network, communication, data consistency, observability challenges. Cost, lower initial setup and infrastructure costs. Higher initial setup and infrastructure costs. More operational overhead for monitoring managing distributed systems. Data management, typically single shared database. Decentralized data management. Each service owns its data, polyglot persistence. Testing, simpler unit testing, complex integration end-to-end. Simpler unit integration testing per service, complex end-to-end, and distributed testing. Operational considerations, beyond development. The architectural choice profoundly impacts how your application is operated once it's live. Logging and monitoring. In a monolith, logs are usually in one place, making debugging relatively straightforward. In microservices, services generate logs independently, requiring centralized log aggregation, e.g., Elastic Stack, Splunk, and sophisticated monitoring tools, e.g., Prometheus, Grafana, Datadog, to stitch together a coherent picture of system health. Debugging a monolithic application means stepping through code within a single process. In a microservices environment, a single user request might traverse multiple services. Tracing that request across these services requires specialized distributed tracing tools, e.g., Jaeger, Zipkin, to understand the flow and pinpoint issues. Deployment pipelines, CI/CD. While a monolith has one, potentially complex, deployment pipeline, microservices have many, simpler, independent pipelines. Managing numerous independent deployments and coordinating releases becomes an orchestration challenge, often requiring robust automation and tools like Kubernetes. Network and latency. Monoliths communicate internally within the same memory space, which is very fast. Microservices communicate over networks, introducing latency and the complexities of network reliability. This needs careful design to minimize chatty communication between services. Organizational and cultural impact. Conway's law in action. The influence of architecture extends far beyond technology, impacting your organization's structure and culture. Conway's law states that organizations which design systems are constrained to produce designs which are copies of the communication structures of these organizations. Team size and communication. Monoliths often lead to larger, more interdependent teams or functional silos, e.g., front-end team, back-end team. Changes often require coordination across multiple teams, leading to slower decision-making and increased communication overhead. Microservices encourage smaller, autonomous, multidisciplinary teams, what Amazon calls two-pizza teams, meaning a team small enough to be fed by two pizzas. Each team owns one or more services end-to-end, fostering ownership and promoting faster, more direct communication within the team. Need for DevOps culture. Adopting microservices almost necessitates a strong DevOps culture. Teams must take on more operational responsibility, embracing automation, continuous delivery, and monitoring. This means breaking down traditional silos between development and operations. Skill sets required. Monoliths can often be developed with a narrower set of skills. Microservices require a broader range of skills, including distributed systems design, cloud-native deployments, advanced monitoring, and a deeper understanding of network complexities and resilience patterns. Training and upskilling developers become crucial. The no one-size-fits-all philosophy. After this comprehensive comparison, the most crucial takeaway should be abundantly clear. There is no single best architecture. Neither monoliths nor microservices are inherently superior. Your architectural choice must be a tactical decision driven by your unique context. Factors to consider when making your choice include team size and skill set. Do you have a small, junior team or a large, experienced team with distributed systems expertise? Project complexity and domain understanding. Is your application small and well understood, or is it a sprawling, complex system with evolving requirements? Budget and resources. Do you have the financial and human resources for the increased infrastructure and operational overhead of microservices? Time to market. Is rapid initial deployment and minimal friction more important than long-term scalability and flexibility? Future growth and scalability needs. Do you anticipate exponential growth requiring highly optimized scaling for specific components? Business agility requirements. How quickly does your business need to react to market changes and deliver new features? Myth busting, dispelling common misconceptions. Finally, let's address some common myths that often cloud this discussion. Myth 1. Monoliths are always bad, microservices are always good. False. A well-designed, modular monolith often outperforms a poorly implemented microservices system across many metrics, including maintainability and operational efficiency. Monoliths are simpler where simplicity is paramount. Myth 2. Microservices will solve all our problems. Microservices address some problems, scalability, agility, by introducing different problems, operational complexity, distributed data management. They trade one set of challenges for another. Myth 3. You must start with microservices. For many, if not most, projects, starting with a well-factored monolith and iterating towards microservices as the business and technical needs demand is a far safer and more pragmatic approach. This is often called a modular monolith. The choice between a monolithic and a microservices architecture is a strategic business decision, not just a technical one. Understanding the trade-offs, advantages, and disadvantages of each in the context of your own organization and project is paramount to charting a successful architectural path. Chapter 5. Why transition? Recognizing the need for change. By now, you should have a clear understanding that neither a monolith nor microservices is universally better. The ideal architectural choice is deeply influenced by an application stage, its scale, the team's capabilities, and the business's goals. However, many organizations find themselves in a position where their initial architectural choice, often a monolith, is no longer serving their needs effectively. This chapter explores the signals that indicate a transition might be necessary and the business drivers that make such a significant architectural change worthwhile. Signs your monolith is becoming a burden. Just like a beloved car that once served you well but now constantly breaks down, costs a fortune in repairs, and guzzles gas, a software application can reach a point where its limitations outweigh its utility. Here are common warning signs that your monolithic architecture might be hindering your progress and becoming a burden. Slow deployments and long build times. A telltale sign of a struggling monolith is when a simple change requires hours to build, test, and deploy the entire application. What used to take minutes now takes an hour, then several hours, and eventually days. This significantly slows down the pace of innovation and makes frequent releases impossible. Difficulty adding new features. As the codebase grows, it becomes harder for developers to understand the entire system. Adding a seemingly small feature might require navigating a maze of interconnected code, risking unintended side effects, and costing far more time and effort than anticipated. This leads to slower time to market for new functionalities. Frequent, unpredictable outages. The single point of failure nature of a monolith means a bug or performance issue in one module can bring down the entire application. If your system experiences unpredictable downtime that impacts all users, it's a critical red flag. Developer frustration and low morale. When developers spend more time fighting with build pipelines, debugging intertwined code, or waiting for deployments than they do writing new features, frustration mounts. This can lead to decreased productivity, a struggle to attract new talent, and even high developer turnover. Inability to scale specific features independently. If your application has certain features that experience disproportionately high traffic, e.g., a popular search function or a viral marketing campaign landing page, but you have to scale the entire application to handle that peak, you're wasting resources. This inefficient scaling is a clear sign that a monolithic approach might be holding you back. High operational costs due to inefficient scaling. Related to the point above, scaling a monolith often means throwing more hardware at the entire application, even if only a small part is resource-intensive. This leads to unnecessarily high infrastructure costs over time. Technology debt accumulating rapidly. In an attempt to patch immediate problems or deliver features quickly, teams might take shortcuts, leading to a sprawling, poorly structured codebase. Upgrading libraries or frameworks becomes a nightmare, further increasing the burden. Long cycle times and technical debt as a bottleneck. If your business is constantly pushing for new features, but the technology team is bogged down by technical debt or slow processes, the business-to-technology gap widens, impacting competitive advantage. Business drivers for architectural change. While the technical warning signs are important, the decision to undertake a transition is ultimately a business one. Architectural changes are expensive, time-consuming, and carry inherent risks. They are undertaken because there's a clear business benefit to doing so. Here are the key business drivers for considering a significant architectural shift, often towards microservices. Need for greater agility and faster innovation. In today's competitive landscape, businesses must be able to adapt quickly, experiment with new ideas, and deliver features rapidly. If your current architecture means new feature releases are monthly or quarterly, while your competitors deploy daily, you're at a disadvantage. Microservices enable smaller, independent teams to work and deploy in parallel, accelerating the pace of innovation. Responding to market demands, e.g., new channels, higher traffic. A successful product often faces increasing demands, more users, new geographical markets, integration with partners, or support for popular new platforms, e.g., voice assistants, wearables. A monolithic architecture might struggle to adapt to these diverse and growing requirements without becoming unstable or impossibly slow to change. Attracting and retaining talent. Modern developers are often drawn to companies that work with cutting-edge technologies and modern architectural patterns. Continuing to work on an aging, complex monolith can make it harder to recruit top talent and retain experienced engineers, impacting your ability to innovate. Reducing operational costs, long-term efficiency. While the initial infrastructure costs of microservices can be higher, optimized scaling of individual services can lead to significant cost savings in the long run. By only scaling the components that are under load, organizations can use their computational resources more efficiently when operating at scale. Competitive advantage. Ultimately, all these factors roll up into competitive advantage. A more agile, resilient, and scalable software system allows a business to outmaneuver competitors, capture new market segments, and deliver superior customer experiences. Improved system resilience and customer experience. As customer expectations for always-on, high-performing systems grow, the cost of downtime increases. If your business cannot tolerate system-wide outages and needs high availability, the fault isolation benefits of microservices become a critical business requirement. Avoiding the hype-driven development trap. It's crucial to distinguish between genuine business or technical needs and simply chasing the latest technology trend. Before embarking on an architectural transition, ask yourself, what problem are we really trying to solve? Is it slow development, scalability, reliability, or team morale? Is an architectural change the only solution? Sometimes, simply modularizing your existing monolith or improving your testing and deployment pipelines can address many of the pain points without a full-blown transition. What are the measurable benefits? Can you quantify how this transition will improve key metrics like release frequency, uptime, or developer satisfaction? What's the cost-benefit analysis? Architectural transitions are expensive, both in terms of financial investment and the effort, time, and potential disruption they cause. The anticipated benefits must clearly outweigh these costs. An organization should not transition to microservices just because everyone else is doing it, or because it sounds modern. For example, a small startup with a niche product and limited funding should likely prioritize market validation and rapid feature delivery with a monolith over the complex operational overhead of microservices. Establishing a clear vision. Once you've identified that an architectural transition is genuinely needed and justified by clear business drivers, the next step is to establish a clear vision for the change. What do you hope to achieve? Be specific and measurable. For instance, reduce our average feature delivery time from 3 months to 2 weeks. Achieve 99.99% uptime for core services. Enable independent teams to deploy their features multiple times a day. Reduce our cloud infrastructure cost for peak load by 30%. Having a well-defined vision will serve as your guiding star throughout what can be a challenging, but ultimately rewarding, architectural journey. Recognizing why you need to change is the critical first step towards a successful transformation. Chapter 6. Strategies for a smooth transition. From monolith to microservices. Once the decision is made to transition from a monolithic architecture to microservices, the next critical question is how. The term transition implies a journey, not a sudden leap. Attempting a big bang rewrite, scrapping the entire monolith, and building a new microservices system from scratch is almost universally discouraged. Such projects are notoriously risky, often fail, and leave businesses without a functional product for an extended period. Instead, successful transitions employ evolutionary, incremental approaches. The core philosophy is to chip away at the monolith, piece by piece, while the existing system continues to function and deliver value. This minimizes risk, provides continuous learning opportunities, and ensures business continuity. Introduction to transition approaches. Evolutionary over revolutionary. The most prudent approach is an evolutionary one. Think of it as renovating a house while still living in it. You upgrade one room at a time, ensuring it's habitable before moving on to the next. This is far less disruptive than demolishing the old house and building a new one from the ground up, which would leave you homeless for months or years. Key principles for an evolutionary transition include: isolate, clearly define the boundaries of the functionality you want to extract. Extract, move that functionality into a new, independent service. Iterate, repeat the process, learning and refining with each step. The strangler fig pattern, a gradual transformation. One of the most effective and widely adopted patterns for this evolutionary transition is the strangler fig pattern. Coined by Martin Fowler, it draws its name from a type of fig tree common in tropical forests. This fig starts as a small vine that wraps around a host tree. Over time, the vine grows, thickening its trunk and branches, eventually encompassing and strangling the host tree, which eventually dies and rots away, leaving the fig tree standing independently in its place. In software, this analogy perfectly describes the process of gradually migrating functionalities from a monolithic application to new, independent microservices. The new services strangle or replace the old functionality, which is eventually retired. How does it work? The core idea is to intercept incoming requests to the monolith and divert specific functionalities to new services without directly modifying the bulk of the old code. Here's a simplified breakdown. Identify a business capability. The first step is crucial. Pinpoint a well-defined piece of functionality within your monolith that you want to extract. This isn't about arbitrary technical layers, but clear business boundaries. Examples include user authentication, order processing, customer management, or product catalog. Look for areas that are frequently changed, critical for scaling, or cause frequent issues within the monolith. Build the new service. Develop the new microservice from scratch or as a new, clean service to handle this specific business capability. This service will have its own code base, its own lifecycle, its own potentially independent data store, and its own deployment pipeline. Crucially, it doesn't initially touch the old monolith. Introduce a strangler facade or API gateway. This is a new, lightweight layer placed in front of your monolith. This facade, often implemented as an API gateway or a specialized reverse proxy, acts as the gatekeeper for all incoming external requests. Gradual rerouting. When the facade receives a request for the newly extracted functionality, it redirects that request to your shiny new microservice. All other requests continue to be routed to the original monolith. This rerouting can happen gradually. You might start by diverting a small percentage of traffic, e.g., 5% of authentication requests for new users, to the new service. Monitor its performance and stability, and then incrementally increase the traffic over time until 100% of the requests are handled by the new service. This controlled rollout significantly minimizes risk. Deprecate and remove old code. Once the new microservice is fully functional, stable, and handling all relevant traffic, the corresponding code in the original monolith that provided that functionality can be safely removed. You technically strangle that part out of the old system. The old, duplicated code is no longer exercised and can be deleted, ensuring the monolith truly shrinks. This incremental process is then repeated for each business capability you wish to extract. Over time, the monolith shrinks, becoming a smaller, potentially less critical component, or even disappears entirely as all its functionalities are migrated. Imagine an e-commerce platform that started as a monolith. Their order processing module is becoming unwieldy due to increasing transaction volumes and complex integrations. Using the strangler fig pattern, they would build a new, dedicated order service, route all new order creation requests through an API gateway to this new service. As the new service proves stable, they might migrate historical order data or gradually shift other order-related operations. Once live, the old order processing code in the monolith is deactivated and eventually removed. Why is it powerful? Minimizes risk. You're not attempting a massive, risky, big bang rewrite. Each step is small, testable, and reversible if something goes wrong. If the new service has issues, you can quickly revert traffic to the monolith. Continuous value delivery. Your users continue to interact with the system, often unaware of the underlying architectural changes. New features can be built on the new services while the old ones are still running, ensuring business continuity. Learnings along the way. Each extraction helps your team learn more about building and operating microservices in a real-world scenario, without betting the entire company on a single, massive project. This iterative learning is invaluable. Flexibility. You can choose to stop migrating at any point if the remaining monolith provides sufficient value or if the cost of further migration outweighs the benefits. You don't have to go all the way to a pure microservices architecture if a hybrid approach better suits your needs. Branch by abstraction. Another valuable technique, often used in conjunction with or as an alternative to strangler fig for specific situations, is branch by abstraction. This pattern is particularly useful when you're replacing a core component within the monolith rather than just externally extracting it, or when preparing for a transition where the old and new implementations need to coexist for a period. Here's how it works. Create an abstraction layer. Introduce an interface or an abstraction layer in the monolith that defines how the current component is used. All parts of the monolith that interact with this component are rewritten to use this new abstraction instead of directly calling the component. Implement the old and new, both the old component and the new replacement component, which might be a call to a new microservice. Implement this shared interface. Gradual switchover. A configuration flag or feature toggle is used to dynamically switch between the old and new implementations at runtime. This allows for controlled rollout, A/B testing, and easy rollback. Remove old implementation. Once the new implementation is stable and proven, the old implementation and the abstraction that supported it can be removed. This pattern is excellent for managing complexity during internal refactoring or when a specific piece of functionality, e.g., a payment gateway integration, needs a modern replacement. Decomposition patterns. How do you decide what constitutes a business capability from a monolithic blob? This often comes down to decomposition patterns. Decomposition by business capability. This is the most recommended approach for microservices. You identify the core business functions of your application and model services around them. For example, an e-commerce system might have services like product catalog, order management, user account, payment processing, and inventory. Each service is self-contained and focuses on a single business purpose. This aligns with the bounded context principle. Decomposition by subdomain. Leveraging domain-driven design, DDD, this approach identifies discrete subdomains within your business domain and builds services around them. A large e-commerce system might have subdomains like sales, fulfillment, customer service, and marketing, each potentially encompassing multiple business capabilities. Decomposition by technical concerns. This approach is generally less recommended for microservices, e.g., breaking an application into a UI service, a database service, and a business logic service. While tempting, it reintroduces tight coupling between services because a business change would still require modifications across multiple technical services. Database decomposition strategies. One of the trickiest aspects of migrating from a monolith is dealing with its shared database. A monolithic database is a major blocker to service independence. Each microservice should ideally own its data. Strategies include database per service, the ideal scenario. Each new microservice gets its own database. Services communicate via APIs, not by directly accessing each other's databases. This decouples data models and allows technology heterogeneity. Shared database per bounded context. In some cases, a small group of related services might temporarily share a database, especially during a transition. This is better than a single, global database but still introduces some coupling. Eventual consistency. When services need access to data owned by other services, a common pattern is to replicate relevant data asynchronously using events. For example, an order service might receive customer details from a customer service via an event stream, rather than constantly querying the customer service database. This leads to eventual consistency, where data might be temporarily out of sync but eventually becomes consistent. API gateway and service mesh. As you decompose, you'll need tools to manage the communication complexities. API gateway. This acts as a single entry point for all client requests. It can perform request routing, as in the strangler fig pattern, authentication, rate limiting, and other cross-cutting concerns before forwarding requests to the appropriate service. Clients don't need to know about the individual services. Service mesh. For managing inter-service communication between microservices, a service mesh, like Istio or Linkerd, provides a dedicated infrastructure layer. It handles concerns like traffic management, load balancing, service discovery, security, and observability for service-to-service calls, offloading this complexity from the individual microservices. Incremental refactoring. Finally, even within the monolith, foster a culture of incremental refactoring. As you identify potential services to extract, you might first clean up and modularize the relevant code within the monolith, making it easier to cut out later. This continual improvement, making the monolith more modular and easier to understand, sets the stage for future extractions. Transitioning an architecture is challenging, but with careful planning, iterative execution, and the right strategies like the strangler fig pattern, it can be a highly successful and rewarding journey, unlocking greater agility and scalability for your organization. Chapter 7. Navigating the challenges of microservices adoption. By now, the benefits of microservices, scalability, agility, technological flexibility, and team autonomy, might sound incredibly appealing. However, it's crucial to understand that these benefits come with a significant increase in complexity, particularly concerning operational, data management, and security aspects. Moving from a single, cohesive application to a distributed system introduces an entirely new set of problems that must be addressed. Ignoring these challenges can quickly turn the dream of microservices into a tangled nightmare. Operational complexity, the hidden iceberg. While microservices simplify individual service deployment, They drastically increase the complexity of operating the system as a whole. You're no longer managing one application, but potentially dozens or hundreds of independent programs running across a network. Distributed logging, monitoring, and tracing. In a monolith, logs are usually centralized, and monitoring tools can easily give a holistic view. With microservices, each service generates its own logs and metrics. You need sophisticated tools and practices for centralized logging, aggregating logs from all services into a single searchable system, e.g., Elasticsearch Splunk. Comprehensive monitoring, gathering metrics, CPU usage, memory, network I/O, error rates from every service and visualizing them in dashboards, e.g., Prometheus Grafana. Distributed tracing, when a user request flows through multiple services, identifying the specific path and performance bottlenecks becomes challenging. Tools like Zipkin or Jaeger help trace a request from start to finish across all involved services. Service discovery and registration. How do services find each other? When Service A needs to call Service B, it needs to know where Service B is located, its IP address and port. Services need to register themselves when they start up and deregister when they shut down. This requires a robust service discovery mechanism, e.g., Eureka, Console, or built-in Kubernetes features. Configuration management. Each microservice might have its own configuration settings, database connection strings, API keys, feature flags. Managing these configurations consistently across multiple environments, development, testing, production, without errors requires dedicated configuration management systems. Network latency and inter-service communication. While fast, network communication is never as fast as in-memory calls within a monolith. Each call between services introduces latency. Moreover, network reliability is not guaranteed. Services need to be designed to handle intermittent network failures, timeouts, and retries. Deployment orchestration. Deploying a single monolith is one thing. Deploying updates to dozens or hundreds of independent services, often with dependencies, though ideally minimal, requires advanced orchestration tools. Kubernetes has emerged as the de facto standard for managing containerized microservices deployments at scale, but it introduces its own learning curve. Data consistency across services, a new paradigm. One of the foundational principles of microservices is decentralized data management. Each service owns its data. This eliminates the benefits of easy, single database transactions typical in monoliths and introduces the challenge of maintaining data consistency across different services. Dealing with distributed transactions, sagas. If a business operation requires changes across multiple services, and thus multiple databases, you cannot rely on traditional atomic, ACID transactions that span databases. Instead, you need patterns like sagas. A saga is a sequence of local transactions, where each transaction updates data within its own service and publishes an event that triggers the next step in the saga. If any step fails, compensating transactions are executed to undo the changes made by preceding steps. This is significantly more complex to implement and manage than a simple database transaction. Eventual consistency models. For many non-critical operations, immediate consistency isn't strictly necessary. Data can be eventually consistent, meaning it will become consistent over time. This approach relies heavily on asynchronous communication, typically via message queues or event streams, e.g., Kafka, RabbitMQ. However, reasoning about system state when data is eventually consistent requires a different mindset from developers. Increased infrastructure footprint and costs. While microservices promise efficient scaling, the initial setup and ongoing operational costs can be significantly higher than for a monolith. More servers, more databases, more network. You'll likely need more instances of various services, more separate databases, and more network infrastructure to handle inter-service communication compared to a single monolithic application. Need for automation and cloud expertise. To manage the sheer number of services and their deployments, heavy investment in automation, CI/CD pipelines, and cloud infrastructure knowledge is critical. This often requires hiring new expertise or extensive training for existing teams. Tooling and licensing. Many of the specialized tools and platforms required for microservices, monitoring, logging, service mesh, orchestration, incur their own costs, whether open source with operational overhead or commercial licenses. Security challenges, more attack surfaces. Distributing your application across many services also distributes your security concerns. Securing inter-service communication. Calls between services over the network must be authenticated and authorized. This means managing credentials, certificates, and secure communication protocols, e.g., MTLS. API security. Each service's API becomes a potential attack surface. Robust authentication, authorization, and input validation are needed for every service endpoint. Identity and access management complexity. Managing user identities and granting appropriate access across many services requires sophisticated identity and access management, IAM, solutions. Testing in a distributed environment. A new level of intricacy. Testing microservices is fundamentally different and often more complex than testing a monolith. Unit and integration testing. These are often simpler per service due to their small size. Consumer-driven contracts, CDC. As services evolve independently, how do you ensure they don't break each other? CDC testing involves services defining and testing the contracts, APIs they expect from other services. This helps catch integration issues early. End-to-end testing. Testing a full business flow that spans multiple services can be flaky and slow due to network dependencies and service availability. Often, teams rely more on a strong base of unit, integration, and contract tests, complemented by lightweight end-to-end tests or synthetic transaction monitoring in production. Service virtualization. For integration tests, simulating responses from dependent services, service virtualization or mocking, can speed up testing and reduce environment complexity. Debugging and troubleshooting. The needle in the haystack. When something goes wrong in a monolith, you might step through debugger or check one log file. In a microservices system, debugging becomes a distributed detective mission, tracing requests across multiple services. As mentioned, a single user click might generate a flurry of activity across 10 to 15 services. Identifying which service introduced an error or latency requires sophisticated tracing tools. Identifying root causes. An issue might manifest in one service, but its root cause lies in another, indirectly called service. Isolating the actual problem quickly is a significant operational challenge. Vendor lock-in, cloud providers. While microservices promote technology heterogeneity at the service level, the sophisticated tooling needed to manage them, especially orchestration like Kubernetes, managed databases, message queues, can lead to a new form of vendor lock-in specific to cloud providers. Migrating large microservices deployments from one cloud provider to another can be a monumental task. In conclusion, microservices are not a magic bullet. They are a powerful architectural style that can yield immense benefits when applied thoughtfully. However, they demand a deeper understanding of distributed systems, significant investment in automation, operational tooling, and a cultural shift within the organization. Understanding these challenges upfront is the first step toward mitigating them and ensuring a successful microservices journey. Chapter 8. The Human Element, Teams, Culture, and Conway's Law. Software architecture is often viewed as a purely technical discipline, concerned with code, servers, and data. However, perhaps no other technical decision impacts the human organization as profoundly as the choice between monolithic and microservices architectures. This is precisely captured by Conway's Law. Conway's Law. Structure follows organization. In 1968, Melvin Conway postulated, any organization that designs a system, defined broadly, will produce a design whose structure is a copy of the organization's communication structure. In simpler terms, if your organization is structured into separate teams for front-end, back-end, and database, you will likely end up with an application that has distinct front-end, back-end, and database layers interacting with each other. If your teams are divided by product features, your software will likely reflect those feature boundaries. Conway's Law is a powerful predictor. For years, Monolithic structures often mirrored traditional functional silos within IT departments. The shift to microservices is not just a technical refactoring. It's often a strategic move to enable a fundamental change in organizational structure and communication patterns, thereby influencing the very design of the software. Impact on team structure, autonomy and responsibility. Microservices architectures thrive when supported by a particular kind of team structure. Cross-functional teams. Instead of functional silos, microservices encourage the formation of small, autonomous, cross-functional teams. Each team typically consists of developers, quality assurance engineers, and operations specialists, or roles that blend these skills. This allows the team to take full ownership of a specific business capability, from ideation to deployment and operational support. Autonomous teams, you build it, you run it. This philosophy, popularized by companies like Amazon and Netflix, means that the team responsible for building a service is also responsible for its operation in production. This fosters a deep understanding of the service's performance, reliability, and true cost. It eliminates the throw-it-over-the-wall mentality between development and operations teams and dramatically shortens feedback loops. Team size: 2 pizza teams. Often, microservices teams are kept small. Ideally, no more people than can be fed by 2 large pizzas. This size promotes efficient communication, agility, and a strong sense of collective ownership. Smaller teams can make decisions faster and adapt more quickly. This transition requires a significant shift from traditional command and control structures to empowering teams with greater autonomy and responsibility. Technical decision-making often shifts from a centralized architecture team to individual product teams, while still requiring architectural governance. Cultural shift to DevOps. Breaking down silos. The success of microservices is almost entirely intertwined with the adoption of a DevOps culture. DevOps is not just a set of tools. It's a cultural and professional movement that stresses communication, collaboration, and integration between software developers and information technology operations professionals. Why is DevOps essential for microservices? Necessity of automation. With potentially dozens or hundreds of services, manual deployments, testing, and infrastructure provisioning are impossible. DevOps emphasizes automating everything possible, from code commits to production deployments, allowing for rapid and frequent releases. Shared responsibility. The you build it, you run it model inherent in microservices means developers become more responsible for the operability, performance, and reliability of their services in production. This blurs the traditional lines between dev and ops. Faster feedback loops. A strong DevOps culture promotes rapid feedback. Issues detected in production are quickly communicated back to the owning team, enabling fast resolution and learning. Continuous improvement. By continuously monitoring, measuring, and learning from production systems, teams can iteratively improve their services and processes. Organizations transitioning to microservices without embracing DevOps principles often struggle immensely with operational overhead, slow deployments, and unreliable systems. Hiring and skill development, a new landscape. Implementing microservices requires a different, and often more specialized, skill set within the engineering organization. New skills required. Developers need to understand distributed systems concepts, e.g., eventual consistency, fault tolerance, network latency, asynchronous communication, cloud-native patterns, containerization Docker, and orchestration Kubernetes. Operations engineers need to be proficient in infrastructure as code, automation tools, and complex monitoring systems. Training and upskilling. Existing staff will need significant training and support to transition to these new ways of working and new technologies. This investment in continuous learning is vital. Attracting talent. For many modern engineers, working on microservices and cloud-native technologies is a strong draw. Adopting this architecture can help attract and retain top talent, provided the organizational culture supports it. Communication challenges. Balancing autonomy with cohesion. While empowering autonomous teams is a goal, it also introduces new communication challenges. Information sharing across autonomous teams. How do autonomous teams stay informed about developments in other services that might impact them? Robust API documentation, frequent communication, and shared architectural guidelines become crucial. API documentation and versioning. Services communicate via APIs. Clear, concise, and up-to-date API documentation is indispensable. Teams must also establish clear versioning strategies for their APIs to ensure backward compatibility and prevent breaking changes. Establishing common practices and governance. While teams have autonomy, some level of shared understanding and common operating procedures is necessary for overall system health. This can involve choosing preferred technologies for certain tasks, standardizing logging formats, or agreeing on security protocols. Architectural governance aims to set standards and provide guidance without stifling a team's ability to innovate. Leadership role in transition, guiding the ship. Transitioning to microservices is a significant organizational change, and strong leadership is paramount. Championing the change. Leaders must articulate a clear vision for why the transition is happening, focusing on the business problems it solves. They need to secure buy-in across all levels of the organization. Providing resources. The transition requires significant investment in tooling, training, and potentially new hires. Leaders must ensure these resources are available. Managing expectations. Be realistic about the challenges and the time it will take. Celebrate small wins, acknowledge difficulties, and provide psychological safety for teams to experiment and learn from mistakes. Encouraging experimentation and learning from failure. Microservices development is often about continuous learning. Leaders must foster a culture where experimentation is encouraged and failures are treated as learning opportunities, not reasons for blame. Cultural transformation. Ultimately, leaders are responsible for nurturing the cultural shifts required, moving towards greater transparency, collaboration, and a you build it, you run it mentality. In essence, building microservices isn't just about writing code differently. It's about organizing people differently, fostering a new kind of culture, and embracing a different set of challenges. Investing in the human element, your teams, your culture, and your leadership is as critical for a successful microservices journey as any technological decision. Chapter 9: Tools and Technologies. Building and managing your architecture. The architectural choices between monolithic and microservices are heavily influenced by the ecosystem of tools and technologies available. While the underlying principles of software design remain constant, the practical application of these principles is molded by the platforms and utilities at our disposal. This chapter provides an overview of the essential tools and technologies that enable modern software architectures, particularly highlighting their role in the microservices landscape. It's important to note that this isn't an exhaustive list, nor is it a recommendation for specific brands. The technology landscape evolves rapidly. Instead, think of these as categories of tools that address fundamental needs in building and managing complex software systems, especially distributed ones. Containerization, packaging for portability. Regardless of whether you choose a monolith or microservices, containerization has become a cornerstone of modern software deployment. Docker, the most popular containerization platform. Docker allows you to package an application and all its dependencies, libraries, configuration files, operating system utilities, into a single, isolated unit called a container image. This image can then be run consistently across any environment, your local machine, a testing server, or a production cloud. Benefits: portability. Works on my machine translates to works everywhere. Isolation. Containers run in isolated environments, preventing conflicts between applications or dependencies. Efficiency. Containers are lightweight and start quickly, making them ideal for scaling. Consistent environments. Ensures that development, testing, and production environments are virtually identical. For microservices, containers are almost a prerequisite. Each microservice can be packaged into its own container, enabling independent deployment and technology flexibility, as each container can encapsulate its specific language runtime or dependencies without affecting others. Orchestration, managing containers at scale. Running a few containers is manageable. Running dozens, hundreds, or thousands of containers across multiple servers requires powerful orchestration. Kubernetes K8s, the dominant container orchestration platform. Kubernetes automates the deployment, scaling, healing, and management of containerized applications. It handles tasks like scheduling, deciding which server a container should run on; scaling, automatically increasing or decreasing the number of container instances based on demand; self-healing, replacing failed containers, removing unresponsive ones, and restarting services that don't respond; load balancing, distributing network traffic across healthy instances of a service; service discovery, helping services find each other; role in microservices. Kubernetes is critical for managing the operational complexity of microservices. It provides the infrastructure layer that makes you build it, you run it, a practical reality by abstracting away much of the underlying server management. Learning Kubernetes has a steep curve, but its capabilities are almost indispensable for large microservices deployments. Cloud computing platforms, elasticity, and managed services. The rise of microservices is deeply intertwined with the explosion of cloud computing. Cloud providers offer the elastic infrastructure and managed services that dramatically reduce the operational burden of distributed systems. Major players: Amazon Web Services (AWS), Microsoft Azure, Google Cloud Platform (GCP). Benefits: elasticity. Scale computing resources up or down rapidly based on demand, paying only for what you use. Crucial for microservices where individual services might have fluctuating loads. Managed services. Cloud providers offer managed databases, message queues, serverless functions, and other services, removing the need for you to manage the underlying infrastructure. This allows development teams to focus on business logic. Global reach. Deploy your applications closer to your users for reduced latency. Platform as a service, PaaS, and serverless functions. PaaS, e.g., AWS Elastic Beanstalk, Azure App Service, Google App Engine, provides a platform where you deploy your code, and the provider manages the underlying infrastructure. Simplifies deployment for both monoliths and microservices. Serverless functions, e.g., AWS Lambda, Azure Functions, Google Cloud Functions, allows you to run code without provisioning or managing servers. You pay only for the compute time consumed. Ideal for small, event-driven microservices that execute infrequently or for short durations. API gateways, the front door to your services. As discussed with the strangler fig pattern, an API gateway is essential for managing external access to your services. Purpose: single entry point. Clients interact with the gateway, not individual services. Request routing directs incoming requests to the correct backend microservice. Authentication authorization centralizes security concerns. Rate limiting throttling prevents abuse and manages load. Logging monitoring centralizes access logs and metrics. Transformation can modify requests' responses as needed. Examples: Nginx, often used as a proxy; Kong, Apache API SIX, Amazon API Gateway, Azure API Management. Service meshes, managing inter-service communication. While API gateways manage external traffic, a service mesh manages traffic between your microservices. Purpose: a dedicated infrastructure layer for handling inter-service communication. It abstracts away complex networking and provides capabilities like traffic management, routing, load balancing, fault injection for testing. Observability, collecting metrics, logs, and traces for service-to-service calls. Security, mutual TLS, MTLS between services authorization policies. Resilience, retries, circuit breakers to prevent cascading failures. Examples: Istio, Linkerd. A service mesh adds another layer of operational complexity, but can provide immense benefits for large, complex microservices deployments by normalizing and centralizing critical operational functions. Monitoring and observability tools, seeing what's happening. In a distributed system, knowing what's happening at any given moment is crucial. Good observability, the ability to infer the internal state of a system by examining its external outputs, is non-negotiable. Logging, systems for aggregating, storing, and searching logs from all services. Examples: Elk Stack, Elasticsearch, Logstash, Kibana, Splunk, Datadog, Grafana Loki. Metrics, tools for collecting, storing, and visualizing numerical data about system performance and health. Examples: Prometheus, with Grafana for visualization, Datadog, New Relic. Tracing, tools for tracking the flow of a single request across multiple services. Examples: Jaeger, Zipkin, OpenTelemetry. CI/CD pipelines, automating everything. Continuous integration, CI, and continuous delivery deployment, CD, are fundamental to successful microservices adoption. Purpose: automate the entire software delivery process, from code commit to production deployment. For microservices, this means highly automated, independent, and fast pipelines for each service. Tools: Jenkins, GitLab CI, GitHub Actions, CircleCI, Azure DevOps. Benefits: faster release cycles, reduced manual errors, quicker feedback loops, and increased trust in the deployment process. Messaging queues, event streams, asynchronous communication. For loose coupling and handling distributed data consistency, asynchronous communication is key. Purpose: enable services to communicate without direct dependencies, buffer loads, and facilitate event-driven architectures. Messaging queues, e.g., RabbitMQ, Apache ActiveMQ, AWS SQS. Primarily used for point-to-point or publish-subscribe communication where messages are consumed once. Good for task queues or immediate notifications. Event streams, e.g., Apache Kafka, AWS Kinesis. Designed for high-throughput, fault-tolerant, persistent streams of events. Ideal for data replication, real-time analytics, and building event-driven architectures where multiple services might react to the same event. Database technologies, polyglot persistence. With microservices, the old constraint of using a single database technology for the entire application is gone. Polyglot persistence. This is the practice of using different database technologies for different services, choosing the best tool for each specific data storage need. Examples: relational databases, e.g., PostgreSQL, MySQL. Still excellent for structured data where strong consistency and complex querying are paramount. NoSQL databases, e.g., MongoDB, Cassandra, Redis, offer various benefits like schema flexibility, horizontal scalability, or ultra-fast in-memory access, suitable for specific use cases within services. The strength of a microservices architecture is often directly proportional to the maturity and effective application of these tools and technologies. While they enable the benefits, they also introduce a steep learning curve and significantly increase the operational footprint. Choosing the right set of tools and investing in the expertise to manage them effectively is paramount to a successful microservices journey. Chapter 10, Beyond the Hype, Making Informed Decisions. The journey through monolithic and microservices architectures reveals a landscape rich with technical options and strategic considerations. We've seen the advantages of starting simple, the pains of growth, and the complexities of distribution. Now, it's time to consolidate that knowledge and establish a framework for making truly informed, pragmatic decisions, moving beyond the hype. The central theme to carry forward is this: context is king. There is no one-size-fits-all solution, no magical architecture that suits every company, every team, or every project. The objective is business value, and architecture is merely a means to achieve it. When to stick with the monolith? Despite the widespread enthusiasm for microservices, there are many scenarios where a monolithic architecture is not just acceptable, but often the optimal choice. Don't be swayed by trends if your current context doesn't demand the additional complexity. Small, stable applications. If your application is relatively small, has a clear, stable domain, and isn't expected to grow exponentially in complexity or traffic, a monolith is often the most cost-effective and efficient solution. The overhead of managing distributed systems outweighs any potential benefits. Limited team resources. If your team is small, junior, or lacks experience with distributed systems and the associated DevOps culture, attempting microservices too early can lead to significant technical debt, frustration, and failure. A well-factored monolith allows the team to focus on delivering features rather than battling infrastructure. Uncertain domain or early-stage startups. When you're building a new product and the exact requirements, market fit, or business model are still evolving, speed to market and quick iteration are paramount. A monolith allows you to build fast, get feedback, and pivot without investing heavily in a complex distributed setup. The goal is product-market fit, not architectural perfection, when the pain points of a monolith are manageable. If your monolith is modular, build times are acceptable, deployments are frequent enough, and scaling issues are not critical, then the benefits of refactoring to microservices might not outweigh the significant cost and risk of transition. Address the pain points, don't just chase an architectural style. Considering hybrid architectures, the architectural journey doesn't have to be an all-or-nothing proposition. Many successful companies operate with hybrid architectures, leveraging the strengths of a monolithic core while selectively introducing microservices where they provide specific advantages. Monolithic core with isolated microservices for specific functionalities. This is a common pattern for companies midway through a transition, as per the strangler fig pattern, or those with particular, high-demand features. The bulk of the application might remain a monolith, but a traffic-heavy or rapidly evolving component, e.g., a search engine, a recommendation service, a particularly complex payment gateway integration, might be extracted into a standalone microservice. This allows you to get the benefits of scalability or technology flexibility for specific hotspots without rewriting the entire system. Micro frontends. While our discussion has focused mainly on backend services, the concept of microservices can extend to the user interface. Micro frontends break down a single monolithic frontend application into smaller, independently deliverable and deployable frontend applications, each owned by a specific team. This can align front-end development with back-end microservices teams, enhancing end-to-end agility. A hybrid approach can be incredibly pragmatic. It allows you to address specific architectural bottlenecks or business needs without committing to a full-scale, complex microservices transformation that might not be necessary for your entire system. Reversibility and iteration. Architectural decisions are not set in stone. Software development is an iterative process, and architectural decisions should be too. Avoid the mindset that once a choice is made, it's final. The landscape changes, business needs evolve, and teams gain new skills. The importance of continuous evaluation. Regularly review your chosen architecture against your business goals and operational metrics. Are you still achieving the desired agility, scalability, and cost-effectiveness? Building for change, not for perfection, design your systems to be adaptable. Even within a monolith, prioritize modularity, clear interfaces, and loose coupling. This makes it easier to refactor, upgrade, or even extract components later if the need arises. Minimum viable architecture. Don't over-engineer from day one. Start with the simplest architecture that meets your immediate needs and allows for future evolution. You can always add complexity when the pain points clearly justify it. The cost of complexity. Measuring the true investment. The allure of microservices can sometimes overshadow the true cost of operating a distributed system. It's crucial to consider all aspects. Infrastructure costs. More instances, more databases, specialized network infrastructure. Operational overhead. Investment in monitoring, logging, tracing, service mesh, orchestration tools, and the skilled personnel to manage them. Developer training. The significant time and resources required to upskill existing teams in distributed systems patterns, cloud-native technologies, and DevOps practices. Communication overhead. While teams are smaller, inter-team communication needs to be managed effectively through clear APIs and event contracts. Debugging and troubleshooting. The inherent challenges of finding root causes in a highly distributed system. Always ask, is the architectural benefit worth the investment in complexity, time, and money? For many projects, the answer might be not yet, or only for specific parts. The importance of architectural governance. While empowering autonomous teams is vital, some level of architectural governance is necessary to prevent chaos and ensure alignment across the organization. Setting standards without stifling innovation. This involves establishing guidelines and best practices for things like API design, logging formats, security protocols, and preferred technologies for common problems. It's about providing guardrails, not a straitjacket. Architectural review boards. In larger organizations, cross-functional architectural review boards can help ensure consistency, share knowledge, and promote reusable patterns across different teams. Their role should be to guide and advise, not to dictate. Shared understanding. The goal of governance is to foster a shared understanding of architectural principles and a common approach to solving recurring problems, leading to a more cohesive and manageable system landscape. Making informed architectural decisions is a continuous process of weighing trade-offs. Understanding your current context, anticipating future needs without over-engineering, and prioritizing business value. It requires a blend of technical expertise, strategic thinking, and a deep understanding of your organization's capabilities and constraints. Chapter 11, The Future of Software Architecture. Where do we go from here? As we've journeyed through the realms of monolithic and microservices architectures, it's clear that the world of software development is in constant motion. What's considered best practice today may be refined, superseded, or contextualized by new advancements tomorrow. This chapter looks ahead, exploring emerging trends and reinforcing the timeless principles that will continue to guide successful software design, regardless of the specific architectural style in vogue. Emerging trends. Beyond monoliths and pure microservices, the architectural landscape doesn't stand still. New paradigms are continuously emerging, often building upon or refining the lessons learned from both monolithic and microservices approaches. Serverless computing functions as a service FaaS. This takes the idea of microservices to an even finer granularity. With FaaS platforms like Oz Lambda, Azure Functions, or Google Cloud Functions, developers write small, single-purpose functions that execute in response to events, e.g., an HTTP request, a message in a queue, a file upload. The cloud provider fully manages the underlying infrastructure, meaning developers don't provision or manage servers at all. You pay only for the compute time consumed by your function. Implications. Further reduces operational overhead for specific workloads, enables extremely rapid scaling for event-driven scenarios, and can achieve near-zero costs for idle systems. However, it introduces new challenges around cold starts, vendor lock-in, and debugging distributed functions. Event-driven architectures, EDA. While discussed briefly in the context of data consistency, EDA is a broader architectural style becoming increasingly prominent. In an EDA, services communicate primarily by producing and consuming events, rather than direct API calls. Implications. Promotes extreme decoupling, enables real-time responsiveness, and is highly scalable. It shifts complexity from individual service coordination to managing event streams and ensuring reliable event delivery and processing. Apache Kafka is a popular technology enabler for EDAs. Edge computing. As more data is generated at the edge, devices, sensors, and local environments, there's a growing need to process and store that data closer to its source, rather than sending everything to a centralized cloud. Implications. Reduces latency, conserves bandwidth, and enables offline functionality. This introduces fascinating architectural challenges for synchronizing data and managing code deployment across a geographically distributed network of devices. AI/ML integration in architecture. The increasing prevalence of artificial intelligence and machine learning models means that traditional software architectures will need to evolve to support the lifecycle of these models, from data ingestion and model training to deployment, serving, and continuous retraining. Implications. Requires robust data pipelines, specialized compute resources, and new monitoring paradigms to ensure model performance and prevent drift. These trends often blur the lines between traditional definitions. A serverless microservice is essentially a highly refined microservice. An event-driven monolith might use event streams internally to improve modularity. The future will likely see more hybrid patterns and specialized architectures tailored to very specific problem sets. Continued evolution of microservices. While new paradigms emerge, microservices themselves will continue to evolve, becoming more mature and easier to manage. Refinements in service mesh and observability. Tools like Istio and OpenTelemetry are constantly improving, making it easier to manage inter-service communication, security, and gain deep insights into distributed systems with less manual effort. New deployment strategies. As orchestration platforms like Kubernetes mature, new deployment patterns and tools will emerge to simplify complex release processes, canary deployments, and automated rollbacks for microservices. Focus on cost optimization. As organizations mature with microservices, the focus will shift from just adoption to optimizing the operational costs, leveraging various cloud pricing models, right-sizing resources, and improving efficiency. The enduring value of good design principles. Despite the rapid pace of technological change, certain foundational engineering principles remain timeless. These principles transcend specific architectures and technologies, forming the bedrock of any well-designed system. Separation of concerns. Each part of a system should have a single, well-defined responsibility. This makes components easier to understand, test, and modify. Whether it's a module in a monolith or a dedicated microservice, this principle applies. Modularity, breaking down a complex system into smaller, manageable, self-contained modules. This is the essence of both a well-factored monolith and microservices. Cohesion, the degree to which elements within a module or service belong together. High cohesion means a module focuses on a single task or concept. Loose coupling, minimizing dependencies between modules or services. Changes in one component should have minimal impact on others. This is a primary driver for microservices. Domain-driven design, DDD. Concepts like bounded context are invaluable regardless of whether you're building a monolith or microservices. Understanding your business domain and explicitly modeling its boundaries helps create maintainable and understandable systems. DDD focuses on solving business problems, not just technical ones. These principles act as a compass, guiding architects and developers to build robust, maintainable, and scalable systems, no matter what new technologies arrive. The human-centric view of architecture. Looking ahead, it's increasingly clear that software architecture is as much about people as it is about technology. Empowering teams. Future architectures will continue to emphasize creating environments where development teams can be productive, autonomous, and focused on delivering business value. Fostering collaboration. While autonomy is key, collaboration across teams, especially regarding shared component ownership, API contracts, and architectural governance, remains crucial. Continuous learning. The pace of change demands a culture of continuous learning and adaptation. Organizations and individuals must be comfortable with ambiguity and committed to constantly acquiring new knowledge and skills. Adapting to change. The only constant in the world of software is change. New business requirements, evolving user expectations, and technological breakthroughs mean that any software architecture must be adaptable. The goal is not to build a perfect system that never changes, but to build one that can evolve gracefully, absorbing new requirements and integrating new technologies without collapsing under its own weight. Your architectural journey will be ongoing. It's a continuous process of learning, adapting, and making informed trade-offs based on the ever-changing landscape of your business and technology. The principles discussed in this book aim to equip you with the knowledge and mindset to make these difficult but rewarding decisions. Chapter 12. Epilogue. Your architectural journey. We have journeyed through the contrasting landscapes of monolithic and microservices architectures, explored their intricate details, dissected their strengths and weaknesses, navigated the complexities of transition, and peered into the future of software design. As we conclude this exploration, it's essential to distill the multifaceted discussions into actionable wisdom for your own architectural journey. Recap of key takeaways. The guiding principles. Let's reiterate the most crucial insights from our expedition. No single best architecture. This is perhaps the most vital lesson. There's no inherent superiority of a monolith over microservices or vice versa. both are powerful tools designed for different jobs and contexts. Eschew dogma and embrace pragmatism. Context is king. The optimal architectural choice is always contingent upon your unique circumstances, your team's size and expertise, your organization's culture, the application's current stage and complexity, your business needs, and market demands. Evolutionary approach is preferred for transitions. Attempting a big bang rewrite from a monolith to microservices is fraught with peril. Incremental, low-risk strategies like the strangler fig pattern allow for continuous learning, minimize disruption, and ensure business continuity. People and culture are as important as technology. Conway's Law reminds us that organizational structure will be reflected in software design. The shift to microservices often necessitates a deeper cultural shift towards DevOps, empowered cross-functional teams, and a you build it, you run it mentality. Neglecting the human element is a direct path to failure. Microservices introduce complexity. While they solve problems like scalability and agility for large systems, they introduce new challenges related to distributed systems, observability, data consistency, network latency, operational overhead, and security. Be prepared to address these complexities head-on. Good design principles are timeless, regardless of the architecture. Founding principles like modularity, separation of concerns, high cohesion, and loose coupling remain critical for building maintainable, understandable, and adaptable software. Call to action, practical advice for your path. As you step back into your own projects and organizations, here's some practical advice to guide your architectural decisions. Start small, learn fast. If you're embarking on a new project or an architectural transition, begin with the simplest viable solution. Gather data, learn from your experiences, and iterate. It's far easier to add complexity later when it's genuinely needed than to over-engineer from day one. Understand your existing system thoroughly before changing. Before you consider any architectural shift, gain a deep understanding of your current system's bottlenecks, pain points, and critical business capabilities. Don't start designing a solution until you truly understand the problem. Invest in automation and observability. This cannot be stressed enough. For any distributed system, and even for a growing monolith, robust CI/CD pipelines, comprehensive logging, detailed monitoring, and distributed tracing are not optional. They are foundational requirements. Foster a culture of experimentation and continuous improvement. Architectural decisions are not static. The ability to experiment with new technologies, learn from failures, and continuously refactor and improve your systems is paramount for long-term success. Encourage a mindset of curiosity and adaptation within your team. Prioritize business value. Always bring the conversation back to the business. How does this architectural decision contribute to faster feature delivery, better customer experience, reduced operational costs, or increased revenue? Technical elegance should serve business objectives, not exist for its own sake. Don't fear the monolith or its evolution. A well-factored, modular monolith can be highly effective and deliver significant business value. Not every application needs to be microservices. And if your monolith is indeed struggling, remember that an incremental, patterns-based transition often leads to a more robust and sustainable outcome than a risky, big bang rewrite. Final thoughts: the art and science of software architecture. Software architecture is much more than mere technical implementation. It's an intricate blend of art and science. It requires creative problem-solving, a strategic vision, a deep understanding of human dynamics, and a commitment to continuous learning. The landscape will continue to evolve, presenting new tools, new paradigms, and new challenges. But by mastering the fundamental principles discussed in this book, by understanding the trade-offs inherent in every decision, and by prioritizing the symbiotic relationship between technology and organizational culture, you will be well-equipped to navigate the complexities. Your goal is not to build a specific architectural pattern, but to build a system that is robust, flexible, maintainable, and continuously delivers value to its users and stakeholders. May your architectural compass always point you towards impactful and well-reasoned decisions. The journey is ongoing, and the most exciting chapters are yet to be written.